Hello everyone, I'm Takahiro Okamoto from Okamoto University, Japan. I'd like to talk about high bandwidth current sensor for power application using GaN FEMT. I will first talk about background of technical issues. GaN FEMT feature fast switching capability and low resistance. Short circuit with sun time of GaN FEMT is only few nanoseconds, significantly lower than that of other semiconductor MOSFET. When short circuit fault occurs, short circuit current flows through the device. So the high bandwidth current sensor that can sense a sudden rise in current, such as short circuit current, is essential for power application to prevent device breakdown. Also, here is the layout of the parallel GaN FEMT power loop. The current pulse is opposite each other on the front and back layer. Even small plastic inductance on the power loop cause large switching surges in device. Because the fast switching performance of GaN FEMT results in a large DIDT, so the plastic inductance is usually designed to be small. So high bandwidth and low insertion impedance are required for current sensor. Here you can see current sensing method for power applications. Shunt resistor is widely used as current sensor for power application. However, when shunt resistor senses high frequency current, the parasitic inductance in shunt resistor causes unintended voltage due to LDIDT, and then the accuracy decreases at a high frequency. So shunt resistor is not suitable for GaN applications. The current sensing method includes Rogowski coil. The Rogowski coil consists of an air core coil and integrator. The current can be sensed by the linking the magnetic field created this current to the coil and integrating the voltage between the coil. So we focus on Rogowski coil because of the features of low insertion impedance, isolated, and no magnetic saturation. However, existing Rogowski coil also has two issues. The first one is increase in parasitic inductance. To install the existing Rogowski coil in the system, the current path must pass through the center of the coil. By doing so, the current path becomes longer and narrow. The parasitic inductance on the power loop is increased. The second one is insufficient bandwidth. It is necessary to accurately sense a sudden rise in current, such as short circuit current. Existing bandwidth is not sufficient, so close to 1 GHz is required. So our purpose is to develop a high bandwidth Rogowski coil that does not increase parasitic inductance. This slide shows two prior research of the Rogowski coil that can address about two issues. The first one is low parasitic inductance structure. In this structure, solenoid coil with printed circuit board are embedded inside in opposite current paths. The inner magnetic flux created by the opposite current paths are linked to the coil. So the current can be sensed in the same way as conventional Rogowski coil. On the other hand, the external magnetic flux created by opposite current cancel each other out. So the parasitic inductance of this current path can be reduced, and this structure allows the current path to be widened. The second is high bandwidth coil. This figure shows a side view of the conventional Rogowski coil from this perspective. The coil is shown in blue line, and the magnetic flux is shown in orange. And it is reported that the pitch of the coil is 10 times larger coil line width. So coil can be designed as microstrip line with characteristic impedance. So by impedance matching can suppress power reflection at high frequency and enable high bandwidth. So in our research, we propose a new Rogowski coil that can integrate about two methods: opposite current path coil design with microstrip line. So here is a design concept of the proposed Rogowski coil. The coil designed with microstrip line are embedded inside in the opposite current path in the surface layer. So the proposed Rogowski coil consists of multi-layer print circuit board, and it can be installed vertically in the system. However, it is not enough to simply integrate two methods. To achieve integration, it is necessary to solve these issues. The first issue is electrostatic coupling. High-frequency current flowing in the surface layer may flow to the microstrip ground when an intended current caused by CDVDT flows to the microstrip ground. Potential difference is generated in the microstrip ground. The second is eddy current flows through the vias. The microstrip ground is connected to the vias for ground stabilization. Eddy current can flow to microstrip ground through the vias to cancel out the magnetic flux linked to the coil. So these issues cause microstrip ground instability, which prevent the microstrip line from functioning with an accurate characteristic impedance. So it is necessary to stabilize the ground. So I show you the two approaches for these issues in the next slide. The first approach is the provided electrostatic seal in between the inner layer of the microstrip line and the surface layer of the current path. So proposed Rogowski coil consists of 8-layer print circuit board, and the electrostatic seal is connected each other through the vias to the microstrip ground. So installation point is here, ground or power loop. So in order to maintain the opposite current path, the electrostatic seal is not connected to the first layer but 8th layer. So electrostatic seal prevents electrostatic coupling and makes the microstrip ground stable. The second approach is optimal design of microstrip line ground. First, microstrip coil using layer 4th and 5th layer is designed with characteristic impedance so that the pitch of the coil is 10 times coil line width. And the microstrip ground in layer 3 and 6, these are connected each other through the vias, and it is emphasized that these vias are placed only in the center of the layout to prevent eddy current. If the vias are placed in the side of the layout, eddy current flows to the 3rd and 6th layer like this to cancel out the magnetic flux linked to the coil. This causes ground instability, so it is necessary optimal design of microstrip line, and this can suppress eddy current and stabilizes. So I'll show you the measurement result of the parasitic inductance. Here is a photograph of the prototype of proposed Rogowski coil. The left side is the current path and embedded coil, and right side is integrated using APEC. The parasitic inductance is measured by using this external board because the parasitic inductance of proposed Rogowski coil is considered to be very small, so it is increased by using this external board, and the parasitic inductance is obtained from the difference in parasitic inductance of the current path with and without Rogowski coil shown in this photo. And it is derived from parallel resonance point using this formula. And this graph shows the result and impedance characteristics measured by impedance analyzer. The green shows the result with Rogowski coil, and the parasitic inductance is 3.16 nanohenry using this formula. And the pink shows the result without Rogowski coil and 2.82 nanohenry. So the difference of the parasitic inductance is 0.34 nanohenry. It is only 10% of the parasitic inductance of the power loop, and it is considered to have no significant influence on the power loop. So in this slide, I show you measurement result of the coil. First, reflection coefficient is measured by network analyzer to verify the design coil function as microstrip line with characteristic impedance. So at this time, in this prototype, the characteristic impedance is designed to be about 40 ohms. So 36 ohm resistor is attached at point 1 to match the characteristic impedance of microstrip coil. And 15 ohm resistor is attached at point 2 to match the characteristic impedance of network analyzer. As shown in this Smith chart, it is plotted on the center at each frequency. This indicated that the reflection coefficient is 0 and impedance matching possible. So the design coil function as microstrip line with a characteristic impedance. And this graph shows the frequency characteristics measured by network analyzer. The orange shows the result without impedance matching, and the blue shows the result with impedance matching. By impedance matching at point 1, 2, suppress resonance characteristics and improve high bandwidth, and it is also a gain increase. So this cause impedance matching at point 1 impedance from this perspective it become constant. So the resonance characteristic caused by quarter wavelength of the coil length can suppress, and by impedance matching at point 2 allow to power reflection can be suppressed, and allow the power to be transmitted without attenuation. So by impedance matching higher bandwidth. So this slide shows summary. So in our research, we propose a new Rogowski coil that integrates two methods: opposite current path and coil design with microstrip line. And the effectiveness of the prototype of proposed Rogowski coil can be demonstrated through experiment. So in my presentation, I would like to conclude. Thank you for listening.